Yeah, so I'm mainly want to talk about galaxies today. And so this is the title that I choose, A Deep View on the Early Universe. So I'm going to talk a lot about distant galaxies as well, extreme makeovers and overweight galaxies. And my title is like you see this nice artist illustration of how it would look like if you would live on a planet in a galaxy in the early universe. So when the universe was still very young. And what you see here is that the sky is filled with stars. It's much brighter than the sky we see today. I already got the remark, obviously, this is an unpolluted planet. But I hope throughout my talk it will become clear why the sky would look like this. But let's start very simple. Let's start with the object that we all know. That's the Earth. I want to put galaxies into a broader context, like how big are they actually? So we all know the Earth. We know the Earth is actually quite big. It takes a long time to fly from the other side to the one side to the other side. But the planet, our planet, Earth, is actually quite small compared to other planets in our solar system. So here you see an overview of all the different planets in our solar system, and they're scaled by size. I don't have a laser pointer, but you see, I think you'll all see where the Earth is. So the Earth is definitely not the smallest among our planets, and you see also some other objects which are not classified as planets anymore, but it's definitely not among the biggest planets. But if you then compare the Earth to the Sun, our Earth is really tiny. So you've probably all seen these images before. They're all NASA images. So you see there, zoom in, there's the Sun, there's Jupiter, and then the tiny, tiny little dot is the Earth. So the diameter of the Sun is about more than 100 times more than the diameter of Earth. So the Earth is really tiny compared to the Sun. But then, our Sun, our solar system, live in our galaxy, in our Milky Way. So how does that compare? So here you see our Milky Way. And our Sun, or our solar system, is somewhere at the outskirts of our Milky Way. And how you can compare it is the Sun compared to the Milky Way is the same as a football compared to the Sun. Like just a football on Earth compared to the Sun, and we saw how big the Sun is. That's the Sun compared to our Milky Way. So the Milky Way is huge. The Milky Way has hundreds of billions of stars in them. So here you see a really nice illustration of the Milky Way. You see the Milky Way has these nice spiral arms. You see all that blue light. In the middle you see sort of a bulge-like, bar-like structure. And yeah, it looks pretty. But this is obviously not the view that we have of our Milky Way. And why not? Well, because we live in our Milky Way. And we can never see our own Milky Way from far. So where do we live? I already said we live somewhere at the outskirts. We live somewhere over here or there. This is obviously more like a view of how we think the Milky Way looks like. And if you're, oh, perfect, thank you so much. So I think most of you have probably been in the southern hemisphere. If you then look at the sky on a really nice night, you can see nicely the Milky Way over the sky. Well, you can only see that at the southern hemisphere, and then you're looking at the center. But unfortunately for us, we're looking at the outskirts, so if we're here, then we're seeing this part. So it's less obvious, it's less bright. So that's definitely, if you haven't been to the southern hemisphere, it's definitely worth a trip. Okay, so as I said, this is how we think the Milky Way looks like. Because we live in the Milky Way, we can study the Milky Way in a lot of detail. We can see a lot of things around us, but because we're in it, we cannot really see how it would look like afar. So there's also things that we have to infer. So we are inferring, or we think that it has these spiral arms and it has this bulge in this bar, but we're not really exactly sure how it would look like, because this is our view of the Milky Way, of our own galaxy. So this is not a picture that you can take in one shot. This is a picture that you have to take. We're taking all photos from the sky all around the globe and then putting them all together. So this is an all-sky view. And here you see really nicely a full image of the Milky Way. So if you're in the southern hemisphere, you see this part, and we see more these parts over here. So again, you see that bulge that you saw over here. This part, you see that over here. But you cannot really see the spiral arms in that much detail. So that's sort of inferred. So that's why we're not really sure whether there's actually spiral arms. We think there are, but we're not really sure. So you also see, you see a lot of light, but you also see these dark spots over here. That's actually dust. That's blocking the view, the light from the stars, and that's why we don't have a full view. We see these dark patches over here. So the Milky Way, we know a lot about the Milky Way, but it's actually easier to study a galaxy that is not our own galaxy, but nearby. And we probably all know the Andromeda galaxy, especially for those who have a map. This is the standard background. And so this is our closest neighbor, our closest large neighbor. There's some tiny galaxies around us, but this is the largest, closest galaxy. And the distance from this galaxy to our own Milky Way is about 20 times the size of the diameter of the Milky Way itself. So it's actually not that far. But this is, again, a really, really huge galaxy. This also has hundreds, maybe thousands of billions of stars in it. So if you look at this galaxy, and you think back of how we think the Milky Way looked like, they're actually kind of similar, right? They both seem to, the stars seem to be in sort of a disc shape. You saw these spiral arms. There seems to be sort of more light in the center, which we call a bulge. So this may make us infer, like, oh, well, these galaxies all have sort of a similar shape. Andromeda, the Milky Way, do all galaxies look alike? Well, all galaxies have a disc shape and these spiral arms and a bulge. Well, that's not really true, because we also find galaxies like this in our sky. This is M87. Here's where we run out of nice names. And you see that this is actually kind of a boring galaxy. It's not as pretty as these nice spiral galaxies. It's very different. It's actually very remarkably different from the spiral galaxies. So what's one of the differences? Well, this is actually round or elliptical shape, which means it's not flattened. It really has like a 3D dimension. It's like thick in all directions. And you don't really see any structure, spiral arms, over densities in there. It's really a smooth, kind of boring system. And it also has a different color, which I will come back to later. So you see it more as a reddish color, but the other one is more like a bluish, more patchy system. So if you now put them together, you can really see the difference between these two types of galaxies. And I really like this image because this is really a photo on one piece of the sky. So these systems are actually neighbors. And they're completely different, right? So we have again a spiral galaxy with the blue arms. It's sort of flattened. And then we have this elliptical galaxy over here, which is very smooth and very regular and more rounder in shape. So it turns out, which is actually interesting, that almost every galaxy in our universe, you can divide in one of these two groups. They're or more like an elliptical galaxy, or they're a spiral galaxy. So here you see an overview of a lot of our neighbors. And if the first view, what you have if you look at this nice overview is like, wow, there are lots of colors, lots of shapes, lots of different galaxies. But if you really look at them in more detail, you can almost all divide them into or more like a spiral galaxy, flattened spiral, or a roundish elliptical galaxy. So here you see an edge-on spiral. There you see more a face-on spiral. Like how they look like obviously depend on from which orientation you see them. And then there's lots of elliptical galaxies over here. This laser pointer is great. So what is actually more of a difference between these different types of galaxies? So here I zoom in again on 6 spiral galaxies. So as most of you may guess, these beautiful images are obviously all taken with the Hubble Space Telescope, which really lets us take such beautiful images of the sky. So you see there's some spread in properties. Some of them have more like a bar-like structure, but all of them have like spiral arms. All of them look sort of bluish. All of them have sort of a bulgy structure in the center, although how big that is sort of different for each of the spiral galaxies. So why are these systems blue? Well, they're blue because they're still forming new stars. So if you have a lot of new stars that are being formed, then a galaxy appears bluer because you have a lot of very, very hot newly formed stars. Once a galaxy or stellar stars become older, like the bluest, the most hottest stars will die out into supernova, and the lower mass stars remain, and these are red. So a galaxy that's older will be redder, and a galaxy that's younger or has new stars that are being formed is much bluer. And that's why it also looks not very smooth, but you see a lot of like brighter pieces. That's like where there's lots of new young stars being formed. So what else is happening in these systems? Well, they're actually rotating. That's why they're flat and they're rotating. So they're disks that I already said. So the stars are going around the center like that. They're also actually not very heavy. They're not as heavy. So the Milky Way and Andromeda are actually kind of big, but the average spiral galaxy is not super heavy. Like Milky Way and Andromeda are about like the most heaviest, most massive spiral galaxies that we know. Like the more massive galaxies, so the systems that have even more stars are these ellipticals. They usually have many, many more stars than the spiral galaxies. And here you see an overview of the ellipticals. And you see again really nicely the contrast, right? So here they're all more like reddish shape. So that means that these systems actually are not really forming any new stars anymore. So the light is coming from old stars, and that's why these systems look red. And they're very smooth, so you don't see these bluish star-forming regions. They're very smooth, they're roundish, and they're actually not really rotating. Like all the stars are going in all sorts of directions. There's not really like a major rotation in the system. You do see some of them have sort of like a disky thing in them, that's sort of like a disk of dust. But most of them are very roundish, kind of, yeah, sort of boring. So Edwin Hubble, already more than 100 years ago, already noticed this difference between these different types of galaxies, and he classified them into a tuning fork. And here you see the tuning fork. So he said elliptical galaxies are on this side, spiral galaxies are on that side. So the ellipticals come into difference, like how elongated they are, and the spiral galaxies, some of them have more like these barish shape in the center, others don't, but basically it's sort of divided between the spirals and the ellipticals. So we already saw, if we're going to go to this side, the galaxies become redder because you get more older stars. If we're going to go also towards this side, they become rounder, we saw that, and they become heavier. So these galaxies have more stars than these galaxies. These are rounder than these, and these are redder. So what else is different between these two? Well, it's actually in what kind of environment they're living. So the Milky Way and Andromeda are neighbors. As I told you, they're pretty close. I'm not sure if this is really on scale, but here is the Milky Way and like all the tiny little fuzzy neighbors. And here's the Andromeda with the tiny little neighbors. And it's a pretty like normal, maybe even underdense environment. But if you then see where the elliptical galaxies live, it's more like this. See? Just to be fair, this is not a real image, right? This is more like how we think it looks like from afar. But this is a real photo taken with the Hubble Space Telescope. And this is a very, very dense environment in the universe. And you see it's full with these elliptical galaxies. This is what we call a cluster of galaxies.
So all those kind of big circular things, are those lensing effects?
Yes. These are background galaxies that are lensed by this very massive cluster. That's a different one. Probably somewhere in the future or in the past. So if you go back to this Hubble tuning fork, if you go to this side, you also go to more crowded environments or more crowded regions. Okay, so we know that we have this sort of, how astronomers call it, bimodality between the galaxies. We have this blue spiral population, we have this red elliptical population. What we obviously want to know, and what we still don't really understand, is how did these elliptical galaxies form, how did these spiral galaxies form, and how are these classes related to each other? Are they static, or do they maybe go from one to the other? Okay, so how do we study galaxies? We want to study the history of galaxies. We want to understand how they were formed. Well, one thing that we can do is just look at the galaxies around us and see how old are the stars, and then sort of infer it. But that's actually kind of difficult. But then astronomers, well, actually, let's go back to here. And also to the next slide. So astronomers have sort of, on one hand, we have the disadvantage that we cannot really see how long, like, galaxies evolve over time, because our life is about 80 years, and the galaxy here is not even dead, it's still very much alive, and it's already 5 billion years old. So if we look at the sky, we're not going to see a galaxy evolve over time, right? The galaxy is going to stay the same. The only thing you really see change in the sky are like things like supernova. But the galaxies themselves, you don't see them evolve. So that's a disadvantage, but our advantage is that we can actually look back in time. And that's because the light will take some time to reach us. So for example, the sun, it takes us about 8 minutes. So if you look at the sun right now, the light that we're seeing is not the light that it's emitting at this moment. No, we see the sun how it was 8 minutes ago. The closest star is 5 light years away, 4 light years away. So we see the star how it looked like 4 years ago. Andromeda, we see it how it looked like 2.4 million years ago. And we can see galaxies still, like back in the universe, when the universe was only 1 billion years old. The universe is about 13.7 billion years old. And we can even see the afterglow of the Big Bang, the cosmic microwave background. So we can see the universe at all these different snapshots in time. We can really see galaxies at different snapshots in time. So we can really see how the galaxies looked like when the universe was 1 billion years old, 2 billion, 3 billion. We can only see a galaxy at one point in time. We can never see the same galaxies at multiple points. But we can see galaxies throughout the age of the universe. As you can, for example, see in this nice illustration over here from the WMAP satellite. So the universe is about 13.7 billion years old. And we see galaxies over here around us, but we can look all the way back in the universe and see galaxies in these very early stages when the first galaxies were formed. So how do we actually study galaxies? Well, we, as astronomers, cannot really set up an experiment. Well, some of us can if we really have a lab, but most of us are just dependent on the light we're going to observe from galaxies. So we have a telescope, we observe the light, and we interpret. So we cannot really set up the experiment ourselves, we just observe. But we can observe a lot, we can see a lot, because there's a lot of radiation coming from galaxies in all parts of the electromagnetic spectrum. So this is the electromagnetic spectrum as we all know it. There's lots of, so here you see the visible regime, to where our eyes are sensitive. You have the infrared where it becomes hotter, the microwave, we all know that one, UV radiation, X-ray, gamma ray, all these types of radiation we receive from galaxies. But what we want to know is if we, for example, look throughout this view, if we look throughout time and we see all these types of galaxies, how do we know at which distance they are? How do we actually know whether this is a nearby galaxy or a faraway galaxy? Because we're just seeing a photo, right? How are we going to figure that out? So another thing that helps us is that we can actually determine that from the speed of the light. So if a object, galaxy for example, is moving away from us, as you can see here, the radiation or the photons or the light that's coming towards us will be altered in wavelength. If something comes towards us, it becomes bluer. If something moves away from us, it becomes redder. So for example, if something is anyway, let's explain it in a different way. So we also know that the universe is expanding throughout time, right? So the universe was much smaller in the early days and everything is moving away from each other. So we always compare that with with sort of a balloon in which you can put coins on top of it, right? And then you blow up the balloon, and then all the coins will move away from each other, but the coins themselves will stay the same. So you can see the coins as the galaxies that will keep each other together by their own gravity, but everything is moving away from each other. So the universe becomes bigger and bigger and bigger, and everything will move away from each other. And because everything will be moving away, not things that are really close, but things that are farther apart, things will be redshifted over here. So things that are moved away from us, the light that we will see from an object will be redder than the light actually really is. So something may be actually blue light, but because it's moving away so far from us, by the time we see it, it will be red light. So you can also see it like that. So the universe is expanding, and you have a photon over here. And not only these things are moving away from each other, these objects, but the photon will also become longer, will also be extracted. So the wavelength of the photon will become longer as well. And so this is what we call redshift. And from this redshift, we can actually sort of determine how far away an object is, how far away a galaxy is. So we know what the intrinsic light should be, we know what the observed color is, and then we can sort of infer how far it is. Okay, now it becomes a little complicated. So we're all familiar with the spectrum of the sun, right? You see all the different colors from going from UV all the way to the infrared. Well, this is how a spectrum of a galaxy would look like. Okay, what are we looking at here? Well, this is basically the intensity versus the wavelength. And this galaxy has a lot of intensity over here. And this is the light that we can see with our eyes. This is the light we see with our eyes, and this galaxy is very bright in this part that we can see with our eyes. So, but now, this galaxy is not nearby us, because galaxies around us, with our eyes, we can see them really, really well. But this galaxy is not nearby, it's actually really far away. For example, it would be in the universe when it was only 3 billion years old. So then the light has to travel 11 billion years to see us. So how would the light look like then? It would be here. So all the light will not be emitted in the visible anymore, but it will be emitted in this part of the spectrum, which is the infrared, near infrared. So it's more like heat radiation. So if we want to find very, very far away galaxies, and we're going to look with our optical telescope, so the telescope, like our eyes, it's sensitive towards visible light, we're not going to see them. So we have to go to near infrared wavelengths, or infrared wavelengths. And for example, here you see one of the deepest views of the universe, and this is taken with the Hubble Space Telescope. So this is actually not real visible colors what you're seeing here. What you're seeing here is a combination of different infrared colors. So our next generation of space telescope is going to be the James Webb Space Telescope. Probably a lot of you guys have heard about the James Webb Space Telescope. That's the 5 meter. It's going to be great. But that telescope is actually purely infrared, because that's the way how you can look farthest in time. So this is one of the deepest views of the universe, I already said. This is the Hubble ultraviolet field, and if you actually would zoom in with a better resolution, you would see that every little tiny blob here is actually kind of a pretty galaxy. And interestingly, almost everything you see here is a galaxy. It's not a star, they're galaxies. Like here you see a star, I think there's only 2 stars in this field. All these things are galaxies, all these tiny blobs. And all these galaxies will be at a different point in time. So you're seeing different points in time in only one photo. Some of these galaxies may be maybe as far away as that the light traveled, like 13 billion years. Other ones the light only traveled 2 billion years. But we see galaxies at all different points in time. And then using that redshift, what I told you before, we can figure out at which distance they actually are, how long the light actually traveled to us. Okay, so what we're really interested in is how do galaxies actually look like when the universe was much younger? Because by looking at galaxies when the universe was much younger, we can try to figure out how galaxies were actually formed, how these spiral galaxies were formed, how these elliptical galaxies were formed. That's what we want to know. Okay. So I'm mainly now going to focus on the universe when it was about 3 billion years old. That's one of my favorite times. And here you see how elliptical galaxies look like. Well, the first thing you see, the quality is not as good, obviously, as these nice images I showed you before, because it's obviously very far away, so that's why we don't really have the resolution yet to really make really nice images. So it's a little fuzzy. But this gives you an idea if you look at elliptical galaxies when the universe was about 3 billion years old. And you see they're very comparable to elliptical galaxies today. They're kind of like reddish, they're pretty, like how you call it, pretty smooth. There's not a lot of substructure. But, as the title of my talk said, these galaxies are actually not, they're actually not very comparable to elliptical galaxies today. They're actually very different in the fact that they're much more compact. They're much denser systems. So how dense are they? Well, if you, for example, compare them to the Milky Way, for the same number of stars, the Milky Way would be this big, and all these stars of the Milky Way would have been put into only this tiny little part. So they're very, very, very dense systems. All the stars are much more together than they are in the Milky Way, where they're much more spread out. And this is for the same number of stars, for the same mass in stars. And that's why the sky would look something like this. Because there's so many more stars around, and if you would live on a planet when the universe was only 3 billion years old, in one of those elliptical galaxies, then you would see that the sky is completely filled with stars. So to put it into more of a sketch, so if you hear of the Big Bang, near the early universe, like 3 billion years, then this is how elliptical galaxies would look like, and this is how they would look like today. So they get bigger over time, and then you may think like, yeah, but you know, doesn't that make sense? Because galaxies form new stars, so they get bigger over time. Well, there's two things here. First, this is actually compared at the same number of stars, the same mass in stars. And second, elliptical galaxies are red. They don't actually form new stars anymore. So how do elliptical galaxies grow in size without forming new stars? They're very dense in the early universe, and then suddenly they get very fuzzy and big. They get really puffed up. How is that possible? And this is not the expansion of the universe that's doing it, because the galaxies hold together by its own gravity. So the expansion of the universe is not influencing this. So that's our question that we want to know. So this is actually something that's pretty new. So this was only discovered a couple of years ago, and it kept a lot of astronomers busy for a couple of years. But I think we're now sort of there, but we think what's going on. So we actually not only live in an expanding universe, but we also live in a hierarchical universe in which structures constantly merge together. So this is what we call a merger tree. So basically what this means is galaxies on one hand grow by forming new stars, but galaxies also grow by merging with neighbors. So in the beginning of the universe, we did have a lot of tiny galaxies that were still growing by star formation, but they were also merging together to form bigger things. And here you see time is going in this direction, and this would then be like how galaxies were like in the early universe, and they merge together, and then they become bigger and bigger. That's why we call it a merger tree. But this is probably a better way of looking at it. This is a galaxy simulation, or structure simulation. So you see that over time, smaller structures, smaller galaxies merge together to form bigger galaxies. Let's do it again because it's so pretty. So you see like lots of tiny things fall in, and in the end they build up bigger galaxies. So there's actually a lot of astronomers who do this. They simulate the universe on their own computer. They try to understand how galaxies actually form by making simulations like this. And if you look at, if you really look in detail and take very, very deep photos of galaxies, elliptical galaxies around us, you do indeed see that there's lots of tiny substructures around them. Like for example, here you actually see that there's a little neighbor. Here you see there's like sort of fuzzy spiral arms. Here you see some, or tidal arms. Here you see some tidal arms. So it seems that these elliptical galaxies are actually still constantly merging. So the way to make them bigger over time is actually by having tiny things smash into them, and then they're building up the outskirts of them. So this is a kind of a, maybe sort of a more complicated plot, but here you see the density profile versus the radius. And this would be, in gray, you see the more distant elliptical galaxies, and in the colored one, you see the density profile of the nearby elliptical galaxies. And if you actually look at the center, you see that they're actually pretty comparable. But there's a really big difference over here. So what this tells you is that these systems that we see over here, these very, very dense elliptical galaxies, they're actually the cores of the galaxies over here. And these galaxies are really building inside out. So there's lots of tiny little galaxies smashing into this compact galaxy, and they're really building up their outskirts over time. So that's a way to make the galaxy really bigger without really making it much more massive, by putting all the material at the outskirts.
Did you say the cores of the ultra-compact ones sort of become the, or the ultra-compact ones initially become the cores of the...
Yeah, these are the cores of the systems over here, and they're building inside out. They're building up their wings later on.
How much do the cores actually get dispersed?
The cores don't actually get dispersed that much, only a little bit. But it depends what kind of mergers they are. So most of the mergers, most of the collisions with other galaxies will be with tiny things, and the tiny things won't affect the center that much. But if there's really a big merger, then yeah. Well, if you have a big merger, you actually keep it sort of compact. But yeah, the tiny ones, they will really drop the material at the outskirts. Yes?
This image is very helpful. I was wondering, is there also any way to have a point of origin as far as where the central point in the universe would be of the origin of the Big Bang, or the location, or any way we can say over there?
No.
It's just too massive.
We see the afterglow everywhere. It's that's actually probably a different talk to go into the structure of the universe. Is that coming in the future?
Someday.
Not in the immediate future, we could try.
Thank you.
Is the ultimate fate of the universe in a big black hole?
No, it's going to keep on expanding. Accelerating the universe. That's also a different talk. Yeah.
How does the accretion as you go to the right here affect new star formation?
That's actually a really good question. So these systems are not forming any new stars, but it could be that if you have a tiny thing falling in, that you get like a little bit of a burst of new stars being formed. So yeah, that could be. So that could affect it a little bit, but it's not a really big component. But yeah, very good question. Yes?
Do most galaxies have a black hole at the center?
Yes.
Do the elliptical ones have it? And what happens when they merge? Do all the black holes go to the center, or are there small black holes swirling the outskirts of a bigger fuzzy galaxy?
Well, I think that's a very good question too, and I don't think we really know it. We think that the black holes probably merge, but we haven't really seen that. We're trying to detect that in the future. Yeah, it makes sense. Because it makes sense that the black holes actually merge because there's a really tight correlation between the mass of the black hole and the mass of the galaxy. And if they wouldn't, then you would not get such a relation. Yeah.
I will probably talk a little bit next month about how it's massive black holes grow.
Yeah, there's the expert.
That was my question.
Okay.
In the earliest times before any of the ellipticals have formed at 3 billion year mark, are stars just free floating in an interstellar star field without belonging to any galaxy?
No, and then we get to my next point. So, these systems over here, they have a lot of stars, right? And they're already dead, they're already not forming any stars anymore. So we know that there must have been a point at which these stars were formed. And the stars are always formed in the galaxy itself. They don't form in the space itself. They really form within the galaxy or within a gas cloud. So how does this fit in? Like, how do the spiral galaxies that actually do form stars compare to the elliptical galaxies over here? Right? We had the spiral galaxies over here, we have the elliptical galaxies over here. I told you a little bit about how these things look like when they were younger. But what about this? Are these two classes actually related? Do these ones form in their own way? Do these ones form in their own way? So I'm trying to look again at the distant universe to see if I can address that question. So this is how disk galaxies or spiral galaxies would look like if you would go to 3 billion years after the Big Bang. So they look a little fuzzy here, right? But these are also with the Hubble Space Telescope. It's actually kind of a very recent data. But what you can see here is that they're actually more like very clumpy. You can sort of imagine that they're sort of disky, but they have clumps within the disk. So this could be sort of spiral arms. So the disk galaxies, or the galaxies that have star formation, also look quite different from the elliptical galaxies that we see today. They look smoother, and these look much more clumpier. So what we want to understand is how do we actually go from a system over here to a system over here? How do we go to a big, star-forming, clumpy galaxy to a galaxy over here? Well, there's obviously still a question, are these two classes actually related? But we know that these systems, they're already so supermassive in the early universe, and almost every galaxy that's very massive and heavy in our universe today is an elliptical galaxy. So that's why we know that this system must become an elliptical galaxy. We know that. So how can we go from here to here? So this is actually a question that keeps a lot of astronomers busy at this moment. There's lots of theories out there, and I wanted to show you two. So one of them actually thinks, this is again a simulation, what if these clumps that you see here, these clumps here, they all merge to the center and maybe build up a core. They just merge to the center, they coalesce, and they build up a core in the center. And here you see are 3 different simulations with initial conditions, and you see that you end up with a more dense system. So you see that all the clumps here are spread out over the system, they merge to the center, they end up in a core, and here you see it too. So time goes in this direction, and these are 3 different simulations. So this is one theory, but another still very, very popular theory is, for example, if you just have 2 of these galaxies over here, and what would happen if they would merge together? So you have 2 disk galaxies and they merge together. Then you get something like this. This is a movie again, a simulation, by a postdoc who's actually here in Berkeley. See, the 2 galaxies, 2 disk galaxies, they see each other, they merge together, you get these nice tidal features over here. And then they come back toward each other. They first go a little bit out again and then back to gravity is pulling. And then the result could be a round elliptical galaxy. So this is a very popular theory. Like, you have 2 disk galaxies, they merge together and they form an elliptical galaxy. And if you actually look in the sky around us, you do see that galaxies merge, spiral galaxies, like here, nice Hubble Space Telescope image, 2 big spiral galaxies that are about to merge. This one's very popular, very well known, the here another one. And this is actually a kind of a cool overview. Here you see like all different images of galaxies that are about to merge or already merged. And what these people did is they put them into an order which they think it may happen. Obviously, you can only see the galaxy at one point in their lives. So you can never see that for a galaxy. You can only see this for a simulation. It's the same like with redshift. Yes?
How much time was that simulation you saw? How much time passed?
Well, I don't think there's a time thing in there, but that will take probably a billion years. It depends a little bit on how much gas to stars there is and what the ratios are, and yeah, it depends on many factors. Yes?
Well, all the galaxies and the whole universe will emerge into one big crunch eventually, wouldn't it?
No, because in the end they only merge together once they have a gravitational pull towards each other. But then the universe also is expanding. So all the galaxies that are not gravitationally bound toward each other, they will keep on moving away from each other. And things that are gravitationally bound will probably eventually merge. So what you will see is that galaxies that are in a group, that are sort of neighbors, they will probably merge. Like we are going to merge with Andromeda in 5 billion years. That's going to happen. We're moving towards each other. And we'll probably survive. And but then all the galaxies, like our group and then a group that's far away, which they're so far away that we don't have like gravity compared to each other, then we're going to move away from each other and these groups will never merge. And then we will keep on moving away from each other.
So it's not possible the whole universe to merge into one.
No, well that was still unclear a couple of years ago, but now we think that's actually not going to happen.
No.
Yeah. It will get a very sparse place with like lots of very dense pieces and then lots of empty space.
I mean empty, like no dark matter. Like, what about dark matter?
So these galaxies all live in a, now I'm confusing. These galaxies all live in their own dark matter halo. So there's lots of visible matter here, but there's much more matter in a galaxy that you can actually not see, what we call dark matter, which it has gravity, but in the pieces between, there's not going to be dark matter. So the dark matter is all where the galaxies are.
Maybe we should save the questions still.
I'm almost done. Shall I finish it first and then? Okay, so here again, you can only see galaxies at one point in time, right? So this is just different photos, but they're put into an order which we think this might actually happen. But then the big question is, okay, you can merge two big spiral galaxies together, and in the end make an elliptical galaxies, but is that really the case? It looks like in the simulation, but we also have to make sure that the elliptical galaxy is not going to form any stars anymore, and it's going to become red, and that's still a really, really big issue. So we're not really sure whether it's the clump scenario, whether it's this, or whether they really still more have their own, the ellipticals and the spirals, their own like evolution, so that they're not really that related to each other. So still a lot to do for us in the coming years, so you should come back and see what we're going to do, and keep track of all the nice images that Hubble Space Telescope is going to publish in the coming years to come. And I want to end again with this really, really pretty movie, which you can find online if you Google Phil Hopkins. Thank you.
Okay, we didn't have to wait long to ask your questions.
So you talked about the universe where there are a lot of ellipticals, and you showed the picture of the spirals containing maybe they form ellipticals. Where do the spirals come from?
Where they come from, how they form. Yeah, so the spirals actually form if you have a sort of a gas cloud that actually lives in a dark matter halo, and then it sort of collapses. The gas cloud is rotating like this. And if it then collapses, it forms a disk.
So why weren't there spirals in the early universe then?
These clumpy things, may be actually spiral galaxies, they may be disky. But it's not really clear though, like whether you really have disks in the early universe. Like there are at these redshifts, you do actually at these distances, like 3 billion years after the Big Bang, you do see some of the disks. like the clumpy disks. But the spirals as we see them today, we're not really there yet. And like even earlier in time, we're not really sure how galaxies actually really look like. That's still a question we're working on. Yeah.
About halfway through that movie, it almost looked like a new, bigger spiral galaxy was being formed. So could we generalize maybe that that theory that if you have a whole lot of ellipticals that come together, but as a whole they have enough of a circular momentum that they're basically defining, you know, a rotation axis and have to essentially end up spinning around one another, and then get what you need in order to form this more planary structure, this arms spewing out at the end.
Yeah, so like if you, for example, have two disk galaxies that merge together, they can form an elliptical, or they can also actually form a new disk. But sometimes you have more like the elliptical galaxies, and then something falls in, and you can indeed like sort of rebuild the disk again, as you say. But we know in general that because the elliptical galaxies have more stars than the spiral galaxies, that it usually doesn't go the other way around. It's not that you first have an elliptical and then you form a big disk, but you can reform sort of a disk later on. So we think a lot of the spiral galaxies nowadays may not have, like, you see a lot of the stars in the spiral arms are actually younger, so they may have formed later on, exactly how you said it. If something falls in, it settles, there's angular momentum, it settles in the disk.
But also you mentioned a lot of small elliptical galaxies. So you just take a swarm of smaller galaxies that all together essentially have a rotational momentum.
Yeah, that
Wouldn't
depends.
that likely end up in a more spiral formation?
Yeah, that depends on how much, how gas-rich that galaxy is that's falling in. If it's only stars, it's difficult to get that. But if there's lots of gas, you can think that it settles. Yeah. Yes. Oh, we should do that.
We should vote it.
No, you.
Okay, everyone pass that in.
A given galaxy has a certain amount of matter or energy that doesn't change except for radiation, is that correct?
The energy of the galaxy.
Matter plus energy doesn't change, whether it's
Yeah, so-
stars or just gas, right?
Yeah, the stars form out of the gas, so
Right.
they just don't. They
The
just
total
disappear.
energy is conserved. correct?
Yeah, but if there's a tiny galaxy falling in, you obviously inject the energy and you lose energy in the
Okay, so
radiation.
my question is, how are older galaxies heavier? You say they were heavier and redder. How did that happen?
Because they were initially started off in a more dense, heavy environment. So the universe, like maybe you remember that in the one of the first pictures you had like this sort of afterglow of the Big Bang, and you saw there was sort of a patchy structure. So in the very, very early universe, everything was kind of smooth, all the matter, and but there were some little overdensities, and these grew out to become galaxies. So if you start off with something that was like already heavier from the start, then you end up with something that's heavier. If you start up with something that's less heavy in the start, it will be less heavy later on.
So they don't become heavier, they just are heavier.
Yeah, that's actually a good point. You can see that in that one simulation in which you see all this stuff fall together, it just becomes more clustered. You start with something smooth and matter just falls toward each other and becomes more, it's more clustered. First it was all more smooth, but that part was already had more stuff there. Yeah.
Okay. In one of the pictures, sometimes the spiral galaxies are rotating in different directions. Wouldn't that matter? If they were rotating the same way, wouldn't they coalesce differently than if they went this way?
Yeah, good question. Yeah, definitely. Like the way what the differences in rotation compared to each other when they coalesce, like what the final product is of that collision does depend on one hand what the relative rotation is, but it also depends on how they would fall in, what the relative inclination is of the systems, and also what the relative mass is. So yeah, that's
Because
a
I
good
think
point.
if two spirals go on the same rotation and they're on the same plane, they might keep being a spiral, but if they were going in opposite directions or coming from different directions, they'd be more likely to live.
Yeah, these things definitely do play a role. Yeah, that's what the people who, I don't build these simulations, but that's what they try to do. Like they take all sorts of different angles in which they fall in, and and then try to see what the product is. Yeah.
Something about the views. You had a beautiful picture of the Milky Way that you said was taken from all points on the Earth and then put together,
Yeah.
right? What about when you had that tunnel showing back in time of the entire universe, and there was the Dark Ages after the Big Bang? And is that taken in one view, or is that taken in every direction?
That is also, so that image, so actually that one that I showed, I think it's a satellite image actually. So the satellite, obviously you can see the full sky that is orbiting around the sky, but orbiting around the planet. But yeah, that's more like an illustration. But like that microwave background, that one image
Yes.
that you saw, that's also around the whole sky. So you can see that everywhere. So you can see every point in time. You can see it from every point on the planet.
In every direction.
In every direction. Yes.
What would trigger the first star formation? That is, you have these clouds, they're pretty compact, and there's been a dark age, but there've been no stars yet, and now the first stars form. What's understood, if anything, about that star formation, the original star formation?
Well, it started off, like as I said, the universe is really smooth, and you have like little bumps that are a little bit more overdense. These overdensities become more overdense, more overdense, more overdense, and at some point you have so much gas, and also dark matter in a certain part of the universe that it just collapses. And we don't really know, like the first stars are something that are still a mystery to us. There's lots of people who try to simulate it in their computers. We cannot see them. There's no way we can see like how the first stars form. We don't really know whether the first stars are actually already in galaxies or whether that's just a star itself in a cloud that forms. And some people think that they're like huge, they're like really, really massive, much more massive than the stars nowadays, so they also die very quickly again. But yeah, that's a really good point. That's something that lots of people are working on, and also with the James Webb Space Telescope, which will go up in 2018, we really hope to get an even better view of the universe, of like very, very early universe when the first stars and the first galaxies were formed, because that will be really cool.
That's a really interesting puzzle, because you read about the star formation involving a supernova, and there's explosive material coming out, and that condenses a cloud around it and forms a star, or density waves in a spiral galaxy. But those weren't there originally.
Yeah, and we know that there were generations of stars before our first galaxies were formed, because a lot of the heavy elements, like what we are built up, are actually formed in stars. So we know that there must have been generations of previous star formation and supernova explosions that have put metals in our universe. But yeah, it's a really interesting question. I'm following.
How does this fit in with star-burst galaxies?
So these clumpy things that I showed, the clumpy star-forming galaxies, they could be starburst galaxies. Starburst just basically means there's a lot of stars formed at the same time. And a couple of these merging galaxies that I showed you later on, these people would also qualify them as starburst galaxies. So starburst basically when you have more than so many stars formed in a year, then we call it a starburst galaxy. So like the spiral galaxies, more extreme cases, these are what we call starburst galaxies. So lots of stars being formed. So very, very blue galaxies.
Yeah, since the elliptical galaxies are the oldest one, they must be concentrated at the oldest part of the universe then.
But the universe is always the same age as like the universe.
So there should be one area of the universe where all the older ones are, because we're the younger ones. Makes sense?
No, because like the elliptical galaxies just live in a part of the universe where basically the evolution is just accelerated. It just goes faster, probably. That's more we think it happens, because there's more mass there, things collapse faster, and that's why. But yeah, it's not that the age is at the same point in time. The same point in time, you find both blue galaxies, spiral galaxies, and elliptical galaxies. So it's not that the time is different at these two places.
Big Bang happened everywhere.
It's pretty well spread out then, right?
Are we sure about that?
Well, also, if you were there, over here, you'd be looking back in time also. There is no unique place in the universe, at least that's the assumption.
We could do sort of essentially kind of archaeology here and find sort of, that our own galaxy had evolved over time, or we can do the kind of time travel thing and look at that by looking further away.
In an earlier slide, you showed what appeared to be the initial clumps that you said from the early universe became ellipticals. What was the evidence for that?
You mean the evidence whether that's actually going to happen, or?
Well, whether those clumps the clumpy collections that you saw,
Yeah, these galaxies, yeah.
become ellipticals.
Well, the thing is that these galaxies, when the universe was only 3 billion years old, were already really, really massive. So they already had lots of stars. And if you could look back at 3 billion years, and if you look at the most massive galaxies, you see on one hand these elliptical galaxies already, but you see also these clumpy spiral or clumpy disk galaxies. But in the local universe, if we look at all the massive galaxies, we actually find that everything that's very, very massive, at these masses, is already red and more like an elliptical kind of galaxy. So that means that these galaxies, you're not going to lose the mass, right? So they must become elliptical galaxies because they're already so massive at that time. So that's the argument that we think that they must evolve at some point into elliptical galaxies. But when exactly in time that is, whether they first become compact and then bigger, yeah, we don't know.
Why is 3 billion years your favorite time?
That's a time that a lot of people are, well actually I do have a good point for it. That's actually a time in the universe when the universe was most active. That's when most stars were being formed and most black hole mass was being formed. But also there are some practical reasons why people like looking at that time, because it has to do with atmospheric windows. Like as I told you, that we like looking at near-infrared wavelengths if we want to look to the early universe, but you cannot see at all near-infrared wavelengths. There are some parts that you cannot see, so there's particular windows through which we can look, and that's what also makes sort of provincial time intervals for people out of practical reasons. Yeah. So that helps with like things like the Hubble Space Telescope, because they don't have the atmosphere, so they make life for astronomers a little easier.
Okay, well, if there are no more questions, then let's take Marcia.
Milky Way. And how you can compare it is the sun compared to the Milky Way is the same as a football compared to the sun. Like just a football on Earth compared to the sun, and we saw how big the sun is. That's the sun compared to our Milky Way. So the Milky Way is huge. The Milky Way has hundreds of billions of stars in them. So here you see a really nice illustration of the Milky Way. You see the Milky Way has these nice spiral arms. You see all that blue light. In the middle you see sort of a bulge-like, bar-like structure. And yeah, it looks pretty. But this is obviously not the view that we have of our Milky Way. And why not? Well, because we live in our Milky Way. And we can never see our own Milky Way from far. So where do we live? I already said we live somewhere at the outskirts. We live somewhere over here or there. This is obviously more like a view of how we think the Milky Way looks like. And if you're... Oh, perfect. Thank you so much. So I think most of you have probably been in the southern hemisphere. If you then look at the sky on a really nice night, you can see nicely the Milky Way over the sky. Well, you can only see that at the southern hemisphere, and then you're looking at the center. But unfortunately for us, we're looking at the outskirts. So if we're here, then we're seeing this part. So it's less obvious. It's less bright. So that's definitely, if you haven't been to the southern hemisphere, it's definitely worth a trip. Okay, so as I said, this is how we think the Milky Way looks like. Because we live in the Milky Way, we can study the Milky Way in a lot of detail. We can see a lot of things around us, but because we're in it, we cannot really see how it would look like afar. So there's also things that we have to infer. So we are inferring, or we think that it has these spiral arms and it has this bulge in this bar, but we're not really exactly sure how it would look like, because this is our view of the Milky Way, of our own galaxy. Yeah, so I'm mainly want to talk about galaxies today. And so this is the title that I choose, a deep view on the early universe. So I'm going to talk a lot about distant galaxies as well, extreme makeovers and overweight galaxies. And my title is like you see this nice artist illustration of how it would look like if you would live on a planet in a galaxy in the early universe. So when the universe was still very young. And what you see here is that the sky is filled with stars. It's much brighter than the sky we see today. I already got the remark, obviously this is an unpolluted planet. But I hope throughout my talk it will become clear why the sky would look like this. But let's start very simple. Let's start with the object that we all know. That's the Earth. I want to put galaxies into a broader context, like how big are they actually? So we all know the Earth. We know the Earth is actually quite big. It takes a long time to fly from the other side to the one side to the other side. But the planet, our planet, Earth, is actually quite small compared to other planets in our solar system. So here you see an overview of all the different planets in our solar system, and they're scaled by size. I don't have a laser pointer, but you see, I think you all see where the Earth is. So the Earth is definitely not the smallest among our planets, and you see also some other objects which are not classified as planets anymore, but it's definitely not among the biggest planets. But if you then compare the Earth to the Sun, our Earth is really tiny. So you've probably all seen these images before. They're all NASA images. So you see there, zoom in, there's the Sun, there's Jupiter, and then the tiny, tiny little dot is the Earth. So the diameter of the Sun is about more than 100 times more than the diameter of Earth. So the Earth is really tiny compared to the Sun. But then, our Sun, our solar system, live in our galaxy, in our Milky Way. So how does that compare? So here you see our Milky Way. And our Sun, or our solar system, is somewhere at the outskirts of our... So this is not a picture that you can take in one shot. This is a picture that you have to take. We're taking all photos from the sky all around the globe and then putting them all together. So this is an all-sky view. And here you see really nicely a full image of the Milky Way. So if you're in the southern hemisphere, you see this part, and we see more these parts over here. So again, you see that bulge that you saw over here. This part, you see that over here. But you cannot really see the spiral arms in that much detail. So that's sort of inferred. So that's why we're not really sure whether there's actually spiral arms. We think there are, but we're not really sure. So you also see, you see a lot of light, but you also see these dark spots over here. That's actually dust. That's blocking the view, the light from the stars, and that's why we don't have a full view. We see these dark patches over here. So the Milky Way, we know a lot about the Milky Way, but it's actually easier to study a galaxy that is not our own galaxy, but nearby. And we probably all know the Andromeda galaxy, especially for those who have a map. This is the standard background. And so this is our closest neighbor, our closest large neighbor. There's some tiny galaxies around us, but this is the largest, closest galaxy. And the distance from this galaxy to our own Milky Way is about 20 times the size of the diameter of the Milky Way itself. So it's actually not that far. But this is, again, a really, really huge galaxy. This also has hundreds, maybe thousands of billions of stars in it. So if you look at this galaxy, and you think back of how we think the Milky Way looked like, they're actually kind of similar, right? They both the stars seem to be in sort of a disc shape. You saw these spiral arms. There seems to be sort of more light in the center, which we call a bulge. So this may make us infer, like, oh, well, these galaxies all have sort of a similar shape. Andromeda, the Milky Way, do all galaxies look alike? Do all galaxies have a disc shape and these spiral arms and a bulge? Well, that's not really true. Because we also find galaxies like this in our sky. This is M87. Here's where we run out of nice names. And you see that this is actually kind of a boring galaxy. It's not as pretty as these nice spiral galaxies. It's very different. It's actually very remarkably different from the spiral galaxies. So what's one of the differences? Well, this is actually round or elliptical shape, which means it's not flattened. It really has like a 3D dimension. It's like thick in all directions. And you don't really see any structure, spiral arms, over densities in there. It's really a smooth, kind of boring system. And it also has a different color, which I will come back to later. So you see it more as a reddish color, but the other one is more like a bluish, more patchy system. So if you now put them together, you can really see the difference between these two types of galaxies. And I really like this image because this is really a photo on one piece of the sky. So these systems are actually neighbors. And they're completely different, right? So we have again a spiral galaxy with the blue arms. It's sort of flattened. And then we have this elliptical galaxy over here, which is very smooth and very regular and more rounder in shape. So it turns out, which is actually interesting, that almost every galaxy in our universe, you can divide in one of these two groups. They're or more like an elliptical galaxy, or they're a spiral galaxy. So here you see an overview of a lot of our neighbors. And if the first view, what you have, if you look at this nice overview, is like, wow, there are lots of colors, lots of shapes, lots of different galaxies. But if you really look at them in more detail, you can almost all divide them into or more like a spiral galaxy, flattened spiral, or a roundish elliptical galaxy. So here you see an edge-on spiral. Here you see more a face-on spiral. Like how they look like obviously depend on which orientation you see them. And then there's lots of elliptical galaxies over here. This laser pointer is great. So what is actually more of a difference between these different types of galaxies? So here I zoom in again on 6 spiral galaxies. So as most of you may guess, these beautiful images are obviously all taken with the Hubble Space Telescope, which really lets us take such beautiful images of the sky. So you see there's some spread in properties. Some of them have more like a bar-like structure, but all of them have like spiral arms. All of them look sort of bluish. All of them have sort of a bulgy structure in the center, although how big that is sort of different for each of the spiral galaxies. So why are these systems blue? Well, they're blue because they're still forming new stars. So if you have a lot of new stars that are being formed, then a galaxy appears bluer because you have a lot of very, very hot, newly formed stars. Once a galaxy or stellar stars become older, like the bluest, the most hottest stars will die out into supernova, and the lower mass stars remain, and these are red. So a galaxy that's older will be redder, and a galaxy that's younger or has new stars that are being formed is much bluer. And that's why it also looks not very smooth, but you see a lot of like brighter pieces. That's like where there's lots of new young stars being formed. So what else is happening in these systems? Well, they're actually rotating. That's why they're flat and they're rotating. So they're disks that I already said. So the stars are going around the center like that. They're also actually not very heavy. They're not as heavy. So the Milky Way and Andromeda are actually kind of big, but the average spiral galaxy is not super heavy. Like Milky Way and Andromeda are about like the most heaviest, most massive